Hello, it's Ben Holken here, Associate Professor in Mechanical Engineering, and I'm in our Dynamics Lab at our UTS Broadway campus, and the purpose of this video is to demonstrate and showcase some of the rotating machinery equipment that we have and explain something about how tachometers work and how we can collect pulse trains from tachometers, and we can use those to understand the vibration characteristics of rotating machinery in particular. For the purpose of this demonstration, I've just grabbed a fan. It's just a common garden fan that you can buy in any department store or anywhere really, nothing special about the fan. I have attached a piece of retro-reflective tape to the fan one blade here. That's to give me a very bright return signal once per revolution as the fan rotates from my tachometer, which is I've attached rather roughly with a just with a piece of zip tie, and it is connected to an IEP power supply, and the output from the tachometer via the IEP signal conditioner goes to the oscilloscope here. As the fan rotates, the blade passes in front of the tachometer, which has got a laser coming out of the front, and light is backscattered back into the tachometer, and we get a once per pulse signal on the oscilloscope. The green light on the top of the tachometer indicates every time a pulse comes through. If I just stop it again, we can see that green pulsing slows down. And when we have a look at the oscilloscope in a moment, we'll have a look at the pulse train that comes through from the tachometer with that once per revolution pulse. So I'll resume the fan rotation, and here we can see the pulses becoming closer and closer together as the frequency of the fan gets up to steady state, and now they're separated by a consistent amount. We have 50 milliseconds per division on this display. There are 10 divisions, so that's 500 milliseconds or half a second, and we approximately have one pulse per division for the rotation speed of the fan at the moment. And I can use the math function, for example, in the oscilloscope to do a fast Fourier transform on this square wave, and because of the repetitive nature of these pulses, every 50 milliseconds the fast Fourier transform has the form of a series of peaks at integer multiples of the fundamental rotation frequency, which happens to be the highest peak here, the first peak. I'm showing this on a log scale, by the way, at the moment, so these peaks all look very similar in level, and that's what we would expect for a square wave pulse train coming in as our input signal to our FFT. For a sine wave we get one peak, for a square wave we get an infinite number of integer peaks at the fundamental frequency. I'm using the cursor here to extract the frequency at the maximum value in this function, and that happens to be the first peak, and it shows that our frequency of rotation is 21 Hertz. 21 Hertz is approximately 1300 RPM. I've also got, it's actually 1260 RPM to be precise. I've also got with me our stroboscope. This is a system that has a flashing light source, and the frequency at which the light source flashes can be specified using this digital display here. This tells us the RPM actually, and so we've currently got it set to 1319 RPM. I've got some controls on the back here. I can use the big knob to change the frequency coarsely, so I can increase the frequency, for example, to 1500 RPM, reduce it back to 1000 RPM, 800, etc. When I get close to 1300 RPM, then I can use the small knob here as a fine adjustment. And that allows me essentially to synchronize the motion, the flashing, with the motion of the fan. And if I tune this fine control to the same frequency as the fan is rotating, which, as I mentioned, was approximately 1260 RPM. That's the measurement that we were getting from the oscilloscope, so I can adjust this to close to 1260. And then if we look at that fan blade now, we can see it's almost frozen, or it appears to be frozen, because the light is flashing once per revolution, so we see the same blade. Now they're slightly out of sync. That blade is travelling around at a relatively slow rate, which is the difference between the frequency of the light source and the frequency of the fan. The fan speed does vary because this is just an analog motor. It's not a frequency control, it's not a digital motor, and so it does wander slightly up and down. But now I've pretty much got that very nicely frozen at around about 1260 RPM. And we can see that quite nicely there. So those are the sorts of tools and techniques that we use, the pieces of instrumentation that help us to be able to diagnose vibration faults in rotating machinery. To be able to do that, we always need to be able to measure the rotation speed of the shaft, the misbalances in the shaft, the blade passing frequencies of the fan, sometimes the bearing frequency components. These are all related to the RPM, not necessarily integer multiples. In the case of bearing faults, they're non-integer multiples, but for sure we need to measure the RPM, and that's what having these kinds of pieces of instrumentation and capability allows us to do. I've been Ben Holkin, Associate Professor in Mechanical Engineering at UTS in the Faculty of Engineering and IT, and I hope that's been a useful and informative video. Thanks for watching.